There are many types of neural networks. The most basic is where each layer is simply a linear transformation followed by an activation function. You might hear these types of networks referred to as vanilla neural networks, or fully connected neural networks, or feed-forward networks. And these can work really well for some problems. The problem with these plain old neural networks, though, is that they need to process vector inputs. They can't process matrices or tensors or anything higher dimensional like that. And this means that to use them to process any kind of higher dimensional data, like images or videos, you need to flatten that data out into a vector. And by doing that, you throw away a lot of spatial information that they contain. If you think about it, if you were to line up all the rows of pixels of an image end to end, it will be very hard to make out what's in that image, even as a human, let alone as a machine. Because a lot of the rows, they relate to what's in the row above or below to make these vertical patterns. So instead of flattening out the data, we can use what are known as convolutional networks, convolutional neural networks, or CNNs, to process the data without flattening it first. And CNNs are able to take advantage of how features are related spatially. So let's look at a feed-forward network diagram next to a CNN diagram. In both networks, a similar thing is happening. We're combining these input features to make more meaningful representations, and we're doing that in each layer. But the networks are clearly different in the shape of each layer. The feed-forward network diagram shows vectors in every layer. So this is just basically a list of numbers. In each position here, there'll be a list of different numbers. But the CNN diagram, the first image over here, the first vector over here, that represents the flattened input image. And the CNN diagram shows tensors in some of the earliest layers. So you can see that these are not just vertical rows of numbers. They have some depth as well, and obviously some other width. So whereas these are essentially just lists of numbers, these vectors, these are tensors. And the convolutional network has the first layer, this thing over here. This represents the input image, for example. It could also represent any other kind of tensor data. And the convolutional network preserves the spatial information between layers by processing them with convolutional layers. You can see that both the inputs and the outputs of these convolutional layers, which is kind of the difference between these two tensors, you can see that both of them are tensors. So the input to a convolutional layer is a tensor, and the output of a convolutional layer is a tensor. And so the convolutional layer takes this and changes it to this. This is another convolutional layer, and this is another convolutional layer. And then eventually we'll flatten this thing out and turn it into a vector and do linear layers. We'll get onto that later. But remember that so you can see this like input output of a convolutional layer, both are tensors. And remember that the parameters in any layer, even in a linear layer, determine what the layer is looking for. So what parameters you have, that says what patterns am I looking for. And convolutional layers have weights in each layer too, and they are the same shape as what you see in this blue region of the input here. So however many numbers that blue region happens to overlap in the input, that's how many parameters or weights I've got as well. And so the convolutional layer is looking for a particular pattern in that region of the image. What the diagram doesn't show is that we're going to move that blue filter over the input vertically and horizontally using the same parameters to look for the same pattern in different places. And this is called parameter sharing across space. It's useful because that's the nature of how images and other spatial data exist. That is, you can find the same representation of something in different places. So whatever I'm looking for, maybe I'm looking for a face and this is an image. This particular set of weights could represent the weights which look for faces. And I want to look for them over here, and I also want to look for them over here. So I want to use the same weights in different places. So, and that's how we see, that's how our vision works. We look for the same thing in different places. And this is another really important improvement upon feed-forward networks for processing spatial data. Knowing that this is the underlying nature of the data, that the same thing might appear in different places, we can exploit that information in the way that we process the data. And that makes learning easier. It also allows us to use less parameters than a feed-forward network. And that's because if we wanted to use a feed-forward network to look for the same thing in different places, then we'd have to have the same weights in different positions. So if I wanted to, maybe this layer represents, is there a face in a particular part of this flattened out image? Well, if I wanted to look at it in this part here, maybe that's like the first row, then I have to have weights from these values into a particular position. Maybe this is the face activation. And then I'd also have to have the same weights from here up to here. So I'd have to have weights here the same as they are down here. And that would be just duplication of the same parameters. So ideally I'd like to share those across space and not have to have extra memory to store them or extra processing to find what they should be. So the result of applying the filter in each position is a scalar value. That's why it all kind of converges to one single point over here. So that's, yes, a single number comes from the fact that these weights are applied in this position. And then moving the filter vertically and horizontally produces a scalar for each time that filter is placed in a different position. So that creates a grid of numbers, a matrix with 2 dimensions only, height and width. So where does the depth of this next layer come from then? Well, it comes from the fact that we're not just going to use one filter in each convolutional layer, but we're going to use many. And each of them is going to produce a different matrix, and we're going to stack them on top of each other. So the number of different patterns which each layer looks for is the number of channels in the output layer. So there are many more details to how these convolutional layers work mathematically, but I will save them for now. And that should be just kind of a high-level overview of roughly what convolutional neural networks are doing. They're sharing parameters over different regions of space, and they're able to process spatial data without flattening it and throwing out that information.